Good morning, all. I'm kind of happy to hear having me. So, in today's talk, I will talk about Gen AI on the edge, opportunities and challenges. So, from my view, like how I see Gen AI compared to traditional AI, right? I see Gen AI is drastically different, not from technology per se, but with respect to how it is perceived from the end user and how the users are adopting it. So, there's a huge difference between our traditional AI and Gen AI. Typically, if you look at the uh, uh, can you start the timer, please, here? If you look at that traditional AI, right, typically the big organizations, so they kind of use this traditional AI to improve their services to make it better or make it more customized for the user, right from some recommendation algorithm or trying to target the right set of peoples. But whereas in Gen AI, it is completely different. So this Gen AI will be operated by the hands of those common people. So they directly use those Gen AI and improve or they generate a few things. So that is what the major shift where the Gen AI brings into the table here. It kind of makes all the common user to directly use this AI on their day-to-day life. It's kind of touching their life. And when I talk about edge, right, when you think this Gen AI is going to be directly used by the common consumer, then obviously this Gen AI should be there accessible to their hand on the edge devices. So these edge devices can vary from your smartphone or your augmented reality headset or smart glasses, or it could be your car, automobile. So there is set of and IoT, robotics, and it kind of goes on. So these are all those devices where the consumer directly interact with them. So then Gen AI kind of going to make changes over there. So when you talk about what kind of technological challenges which is there in this Gen AI use cases, that is what we are going to talk about, and some of those interesting use cases we at Qualcomm currently working on Gen AI, we'll talk about it. And then in this session, I'm going to kind of cover mainly the why Gen AI is important and some of those opportunity use cases and challenges and solutions. Solutions mean the trend towards a solution because we cannot solve all the problem in the day one. Okay, so before kind of delve into this Gen AI, I thought I will start with a video about some of the Gen AI use cases, conveniently from Qualcomm, where I work.
Or, I can speak to you. And I can turn words into images.
So, yeah, it's a good video. When you look at those use cases, right, if you look at it, it talks about a voice recognition and then text to voice and then text LLM-based use cases, and then on those image generation, painting, and in painting and out painting, these kind of use cases. Right? These are all a lot of NA use cases, which is in the first phase of use, because in the last 6 to 7 months, this is the change which can bring it on the smart phones. So now let's talk about why this AI use cases has to be on the edge devices. When I say the AI should be on edge devices, what I meant is it is not accessing via edge devices. It is about executing that whole AI inference on the edge devices. That is what when I say edge in AI means execution on this AI. So let's take one use case. Let's say in painting, out painting. What in painting, out painting is, it just if you in that as per the demo, right? You take a smaller picture, you wanted to kind of expand the picture, then all those expanded areas kind of did with a generative fill so that it looks lot natural, and then object eraser video, like you could select it and then generate it with that background, which is kind of seamlessly aligns with that original background, right? These kind of features, if you wanted to give it to user, then this user will try to kind of use this feature day in and day out on hundreds of images, right? They take a selfie, they make it better, they make it funnier. It's a lot of time they will use it. So how do we scale these kind of use cases? Whereas if you go with the current cloud, what is the problem we are saying it? So we'll briefly touch upon that. So first thing is, when you look at this GenAI use case, right, they are really big models. Like you might have seen people talk about like 100, 150 billion parameter models, and then it also have memory and compute intensive. So the compute needed and the server capacity needed to GenAI query is much larger than the simple web search query, and approximately it is around 10x more than the compute needs with respect to the regular queries. Now you have lots and lots of applications which will start using those GenAI going forward. Lot from web search, Office Copilot, image creation, coding assistant, chatbot, and whatnot. So then it will be multiplied by the number of different use cases in those GenAI, and then you multiply by the billions of users, right? Everybody now, they directly wanted to use this GenAI for their day-to-day work. So how do we scale? With the current cloud economics, it simply cannot scale. So we need to provide an infrastructure which can scale with this demand for the GenAI. So that is where you need to run this GenAI on the edge. Okay. So if you look at the current GenAI foundational models, right? If you look at this this graph, right, on this horizontal axis, I put the number of billions of parameters starting from 0.1, 1 billion, 10 billion, and 100 billion, and goes to 1000 billion parameters. And then on the y-axis, list of foundational models, which is in that particular range. So if you take a sweet spot within 1 billion to 13 billion models, these are all the areas we can currently address with the edge device market. So then if you look at in the sweet spot, you see a lot of critical use cases are already easily available over there. Starting from text to image, we have seen that in the video, and then NLP model, and then image understanding, video understanding, robotics, all those GenAI use cases can be addressed with this 13 billion parameter. So we can make these use cases can run on those edge devices in a way so that we really do not need to depend on cloud, and then don't need to pay per query. So all those things are there because the end customer will own the hardware, so they can run it any number of times they want. So that is the main difference this GenAI on the edge is going to give to the end customer. Going further, so let's talk about some of those opportunities on the edge. So these opportunities kind of scans across multiple GenAI domains, so multiple use case domains, starting from XR glasses, and then automobiles, laptop, phone, and IoT. So each areas can be touched by this GenAI with different use cases. So let's talk about some few use cases where GenAI could make a difference. So one use case which we currently working on is making this smartphone as a true digital assistant. So if you want to make it a true digital assistant, right? So when we kind of do this survey, the topmost use case which customer would want is writing or composing an email. So which is now possible with this LLM based models. So with in Qualcomm, we kind of put a front end to this LLM model with ASR whisper based model, which will kind of help you to do the voice to text translation, so that you can kind of command your a smartphone to do stuff, to draft an email and stuff, and then this voice can be enhanced with echo cancellation or speaker identification for security, and then this LLM model can be given with a RAG of the kind of retrieval augmentation training we can do with the complete context of this particular email thread, so that it can give you a response in a way fine-tuned to your regular writing style. Then people can easily kind of edit on top of it and use it. So this is one compelling use case which you can make it quickly in the smartphone area. In addition to that, you can do dialogue summary, and then whenever you work on this team meeting conversation, you can do meeting notes and other things can be automated over there. And then now moving on to this automotive, right? So automotive, I think it has a big opportunity in the automotive space with respect to GenAI, because you, as of now, you kind of command now, okay, hey, temperature is high, can you reduce your temperature, switch on the AC, switch off the AC, blah, blah. You'll give this kind of rule-based commands over there. Now that can be completely changed the GenAI. You can give a command something like, hey, so show me the scenic route to my destination covering some of the beautiful spots over there, and then tell me whenever the particular spot is received, give me some history behind the spot. You can give a command like that. Then you have, combined with the navigation system, you can make it really better there. So it makes it really compelling, and then you kind of connect with the system a lot more. In addition to that, let's say, for example, you can even make order, hey, order my favorite food from restaurant by right in time I reach home. So now this mobile will know when you are starting from office, how much time you take to home, then accordingly it can place the order. So it makes this lot useful and connected. In addition to that, whole this ADAS improvement drive policy, right? That can be improved by using GenAI to identify what are those agents by predicting their next move and stuff like that. So now moving on to the next business use case. The next one is the drive for personalization. So this is very important on the edge use cases, right? So now ChatGPT, lot more people are familiar with the ChatGPT, and they are kind of using it day in and day out. But the one thing which kind of lacks in that LLM models is the contextual information of that particular query. So what I mean by is, let's say I ask a particular query to ChatGPT compared to my teenage son who is kind of asking the same query, but the answers are exactly same. But then it has to be a little different because the context and then emotional intelligence of that particular person needs to be taken into the account before answering that particular query. For example, hey, I'm in Bangalore. Hey, what to do for this particular weekend? What I do on a weekend is completely different from what my son will do on the weekend. So then now you're asking that question in your smartphone, then it needs to understand the contextual and emotional intelligence of that particular person, and then do prompt engineering on the fly, and then ask a question so that it can give different answer based on the person. So that is very, very important for making this ChatGPT or this language models useful for the end customer. So that is where we kind of work come in picture on the smartphone market. So when you look at your smartphone, right, you have a lot of personal information currently available in your smartphone, right from your calendar, whether what is your activity, or you're a fit person, you go for jogging every day, and what is the things you could do, you go for like what kind of recreational activity you do. So all those information is currently available with your calendar, with your email, and with your smartwatches and everything, right? So now it can use those information, and these information can reside within the mobile itself, so that your personal and security information does not need to go to the cloud, and do the prompt engineering of those input text, and then give you a customized response for each people, rather than giving the same monotonous response of somebody asks the same phrase, it gives same answer as long as the seed value is same. So that has to change, and that will be done by on the mobile side using this context personalization. So moving on, so let's briefly talk about some of those key challenges to bring this GenAI on edge. So I put some of those top items, and solutions I put a little bit there, but I didn't put solution for everything because we have a 30-minute slot. I couldn't cover all of them. So the model size is one a big area, because you have shown that the GenAI models are really big. So how do we ensure these models are fit in a small form factor like your smart glass or your phone or an IoT device? And then memory bandwidth. So another thing which is a little bit different from the other machine learning or the traditional AI is, right? So this GenAI or GenAI networks, they are a lot more memory bandwidth heavy than the compute heavy. So when it is slow because it takes more time to transfer the data from your hard disk or your SSD to the DRAM, and then from the DRAM to this internal caches available in your processor chips. So the memory bandwidth becomes more bottleneck compared to even the compute bottleneck. We don't spend that much time on the compute, but then more time on the bandwidth. So how do we solve those memory bandwidth problem? And then compute. So compute, then you cannot definitely use the traditional CPU or GPU on those devices. You need a custom AI-based accelerator to get things really fast so that you can kind of meet that latency requirement. And then power is very, very important there, because you do not want the battery to run out. And then as well as if you are talking about having all the use cases running on edge, right, then it has to be really smaller power compared to the cloud services, right? because cloud service now it takes a lot of tons of power. And then personalization, we talked about some of the examples of personalization. So then to understand those knowledge, right, it need to run some compute. So how do you kind of run those efficiently? These are all the main key challenges which is currently there when we wanted to bring this GenAI on the edge. So let's talk about one of the solution which will kind of help you to make things a lot better. That is called quantization. So this is an important technique to bring any AI models to run efficiently on a edge devices. So typically all these models are FP32. So each parameter, let's say it's 100 billion parameters. So what does 100 billion parameter mean? That means you have 100 billion floating point numbers are there, and each floating point number is a 4 byte in size. So if you take a Llama 7B model, that means 7 billion parameter, and then 1 billion approximately equal to like a 1 GB. So then you multiply by 4, you have 28 GBs of memory you need to run a Llama 7B on your device. Then you need to have a DRAM of 28 GB, or you need to do some page in and page out of it. So it's take a lot of time. So how do you kind of reduce that memory footprint? So without losing that accuracy, that is where the quantization comes to picture. So this technique allows each parameter, which is currently a 32-bit in size, to reduce into all the way into 8-bit and 4-bit. So Qualcomm has been investing in this technology for multiple years, close to a decade, and kind of became a pioneer in this technology. So it kind of converts all those FP32 based parameters into a typical 4-bit or a 8-bit parameters. That way you will get 4 to 8x efficiency on the memory size. So your memory size will reduce all the way from 28 GB to 3.5 GB when you go for a 4-bit based parameter sharing without losing much of an accuracy. So then when you try to reduce it, right, you have to reduce it in a way, say that the distribution spectrum, right? So the distribution spectrum should not be hindered, right? Because your total knowledge is stored in this particular distribution of those weights, and you need to ensure that that relative distance between those weights is in the common terms. So that is what this quantization brings you there. As long as you manage that scenario, then you'll be able to meet those accuracy, and then you can convert all the models into that. So then one more way to kind of look at that quantization analogy, right? You look at the picture, it kind of changes from 24-bit to a single bit, right? You can still see the essence of the picture. People are looking down in a corridor, right? So that you can make it out in all the 24 bits and 8 bits. See, for example, if you wanted to kind of run a model, it wanted to detect the boundary of those people, like that segmentation model, you can very well do it with the input of 8-bit, even for that matter 1-bit pixel, right? You are still not losing. It's the same intuition you can think about when you try to quantize it, just that the amount of intelligence you need to put it so that we don't disturb that relative information available between those weights. So what kind of benefit it can bring down? Direct benefit is it brings down your memory usage from 8-bit to 30-bit. Now we are working on 4-bit and then 3-bit also in future. So that kind of reduces the memory bandwidth so that you can easily move it from there. And then power consumption, right? So now you move from floating to int, and traditionally your int computations are a lot faster and less complex compared to float. So that typically gives you a lot of energy efficiency. If you look at the add efficiency, right? When you try to add a floating point numbers versus int numbers, right? You can do it in a 30x more faster with the 8. And with respect to multiplication, it is 18 times faster than the float. So on memory access also, since you are kind of compressing it in a single cache line, you can bring in a lot more parameters than the previous parameter. The memory access improved. So now with this less memory, your latency is improved a lot. And then since you have a less complex hardware, your silicon size is reduced, which directly proportional to the affordability of that particular chip, as well as the heat management, thermal management, which is also an important feature over there. So this is an important technology which everybody needs to use to kind of bring GenAI into the edge devices. Okay. So the other technology we could use is the hybrid AI, which can be used for the bigger models. So there are a couple of techniques we could use for this hybrid AI. One is a very simple one where you can put the arbitrator on the mobile. and then based on the input prompt, you can either run a rule-based one or a smaller deep learning model, which will kind of identify whether it can be run within the cloud itself or whether it can be run with a device or it may have to be moved to the cloud. So that decision you can make it within the mobile and then make the movement seamlessly between mobile and stuff. And then end user doesn't need to really worry about where it is running, and then it can kind of reduce the number of inferences which need to go to the cloud. So the other one, this is another important technique. So this is like a speculative decoding. Maybe some of you could already aware of it. So where we can run two models in parallel. One is, let's say, 10 times smaller model, which can be run it on the device, and then the regular model, like a 100 billion model or 150 billion model, you can run it on a cloud. With speculative decoding, you first run. So the first problem with this large models, right? So you take a lot of time to move from DRAM to your chip. So typically, it will be done in a batches. You take a particular portion of those weights, you do the computation, and then do a swap and then make it, right? So, and then this inference are sequential. You take first token and then pipe it back and take the second token and pipe it back, you take the same token. So it takes a lot of time to kind of move between the memory and then your storage disk and comes back. But however, if you can keep all those data in memory itself for execution, it makes things a lot faster, and then you can do multiple inferences. So the sequential inferences will happen on this draft model, which will do some 4 co-token prediction, and then that will be given fed as an input to this target model, which could run on cloud, which will kind of check the accuracy of those prediction, and then it will do reprediction only when there is a change between your local prediction and then this cloud prediction. So that will kind of help you there to kind of reduce the number of inferences you run it on the cloud. And typically, as per the analysis done so far, the draft model is able to predict 2 to 3 out of tokens correctly on every 4 tokens identified. So that brings you a lot of advantages with the speculative decoding. So these are 2 advantages. And the third one, which we could focus on, is having a separate accelerator for our deep learning applications. So we can, I just wanted to give some example, can conveniently use our Qualcomm Xen processor, which is an AA processor inbuilt with all the Qualcomm chipset. So this kind of comes with 3 IP blocks. So one is about a scalar and vector, and then you have tensor blocks. So scalar block will kind of help you to do all those control operations to move the data from memory to your tightly coupled DRAM to tightly coupled memory, and then make those controls and parallelizations tests. And then you have this vector that will be fully connected layer. Whole SIMD operations will be done in this vector. And then you have tensor for this matrix-based acceleration. So these 3 IP blocks work seamlessly together, and then they have a commonly available large shared memory, really fast memory. So with this kind of setup, you can have a little bit of more flexibility compared to your GPU or other CPU multi-threading, and then you can still have a lot of advantages in a power efficient manner. So these kind of accelerators is going to really help over there. So to summarize, we will use hybrid AI, we will use AI accelerator, we will use technology like quantization to shrink it out to bring these GenAI use cases on those edge. So this is one small example of how this specific AI processor can make a difference. So this GAN model kind of run with our hexagon processor with commonly available discrete GPU and an eccentric CPU. You can see the speed in which this AI accelerator can make a difference on bringing those inference faster, right? Yeah, so given the time, let me move on. I think you can get the idea of how fast this AI accelerator could be. And then it does with a lot less power. So I want to kind of briefly talk about what I do or what we do in our in Qualcomm software stack, so Qualcomm team. So so we develop the AI software stack for all the edge devices, range from your mobile AR devices to automobiles on ADAS and stuff. So this is our Qualcomm AI stack, which kind of covers starting from the operating system and then system level interfaces and then compilers and math libraries, and on top of it the Qualcomm SDKs. This is called Qualcomm AI Engine Direct. So what it will do is you can train your model on whatever your favorite training network like TensorFlow or PyTorch, then we will take those graph and convert, lower it down to internal IR graph, and then we'll do a lot of fusing, like graph optimization we'll do to make it smaller without losing accuracy, and then we can apply all those quantization level technique, and then we'll run it on our chipset with this whole software stack to run it efficiently on the edge device. Yeah, and this stack is kind of common stack for all the business use cases, and then I kind of covered what are those different segments where this AI stack can be used. So it is truly write once and deploy it anywhere. You have a digital assistant which is developed for mobile, then you can directly take and put it on your car, and then all the way to the server with our AI100 card. Yeah, I think this is what I want to kind of briefly. Okay, that's the conclusion slide. What is the benefit of on-device AI? It reduces the cost because you want the hardware. You don't need to pay per query. Performance will be really good because of quantization technology. Then privacy, because your data sits within your device, does not go to the cloud. Personalization is possible because your data is with your device, and your device kind of closely looking at all your activities, and then it saves lots of energy. Thank you. So that's what I wanted to quickly cover. Maybe I can take a few questions for the panel. Go ahead.
Hello. Hi, so a very informative presentation. So my question is more on use of, let's say, LLM, you've applied quantization, you've done knowledge distillation, you have a smaller model, versus, let's say, having an SLM, which is also going to be specific to, let's say, different, like area of vision, a separate SLM, or text, a separate SLM, versus LLM, which is quantized and having a smaller one. Which way do you see this going on the edge side?
So I think this quantized LLM is the one which is kind of lot friendly for optimization execution. So that is a trend we see it as of now. And then the Llama kind of really a game changer now, because once the Meta kind of delivered this 7B and then this 13B model, right, that kind of really useful for us to kind of fine tune it, make it better. And then now Google kind of delivered Gemini. They have this Nano and other models, which is also we are kind of exploring this multimodality, how it can make difference. So the experiment on this Gemini model is ongoing. However, Llama model is almost like a commercial ready. And then you can still see it in some of those edge devices, like if you buy the Samsung Ultra, right, you can all those stable diffusion and those things, you can definitely see it today. Like you can go to the shop and buy it and then use those use cases. Thank you.
Good morning. Sir, here. I have a two-part question.
Sure.
One is while using quantization, no, almost the effect is reduction of precision. How are you dealing with that? And the second part of the question is, as you're improving your chipsets with these accelerators, is the price of the consumer device going to increase significantly? Yeah.
Okay, so let me answer the first question. So when you try to reduce that precision of those individual parameters, right, so that is going to definitely hurt the precision. So that is why we need to use really innovative algorithms like ADA round, and then you can see DFQ. There are a lot of papers submitted by Qualcomm which kind of details about how do we kind of reduce the precision of those individual parameters without losing this accuracy. You can look at it, and then we strive best to ensure that the accuracy is not really bad. And then most of the Qualcomm-based solutions, right, you can look at all those, like even the stable diffusion which I talked about, where Qualcomm demonstrated less than 1 second image generation, right, that is done in a quantized mode. And then with respect to this price, right, I can diplomatically say that we strive our best to keep the cost same. Thank you.
Competitive kind of question. So Apple has recently posted that they are also trying the same thing to run like a large action model kind of thing,
yes,
approach than a language model kind of thing, focus on. So they published a paper called Flash Memory LLM.
Yeah.
So is it they are going in the same direction as you guys are going, or that's a kind of a different approach what they're taking currently to deal the same problem?
So I think this should be the approach which Qualcomm does is kind of giving results and then giving the results right now. So the people need to go for quantization technology that need to do. And then the recent Apple paper on those flash memory automation, right? That's an interesting paper, so where it kind of talks about how to efficiently move portions of the data from your disk to memory in a efficient, in a predictable manner, so that it can run faster. So that is also a good technology. We will also kind of exploring that. So these technologies are not contradicting each other. They can kind of complement each other. For example, you currently we say 13 billion model, right? Then we can in the future we can take a 30 billion model and quantize it and still use the other technology from Apple, right? So then they can make the addressable size of those generative model little larger. So it is not a competing, I would say, complementing technology.
Oh, thank you.
Thank you. Can you, so the other also can.
So you have walked us through a lot of automation in the slides. So what were the models that were powering that automation?
No, I didn't talk about automation. I was talking about automobiles. So some of them are proprietary. I can talk about, but then we can see we will use what are things we can publicly say is we use the llama-based models for the LLM use cases, Whisper-based model for ASR, and then a lot of foundation models we will kind of use it over there, and then we kind of fine-tune it. So Gemini Nano we are exploring. It is not productized yet. Thank you. Okay. Thank you all for your time. Hope you enjoyed it. Thank you.